Trent Martin, the Johnson Space Center's project manager for the Alpha Magnetic Spectrometer, is here with us in Mission Control today for an interview. And so, welcome in, Trent.
Thanks, I appreciate it.
Great to have you here today and to talk about AMS, as we call it, on the International Space Station. Can you start off telling us a little bit about what an alpha magnetic spectrometer does?
Sure. The alpha magnetic spectrometer is a high-energy physics experiment that was built by a collaboration of 60 different institutes from 16 different countries and led by a Nobel laureate from MIT that combines a system of state-of-the-art high-energy particle physics detectors to sift through the particles that are constantly bombarding the Earth. We do it in space simply because most of these charged particles would not make it to the ground. So the space station provides that perfect test bed for us to utilize and actually measure these particles as they come through the detector. The detector looks for what type of particles we have, so you can tell the difference between a helium atom or an anti-helium atom. The main science that we're looking for is antimatter science, dark matter science, and other cosmic ray propagation in the universe.
And I got to ask you, why should I care about dark matter and antimatter and all those cosmic rays?
Well, AMS is a detector that's essentially designed to probe the foundations of the universe. So the data that we'll gather from AMS, we will utilize for years to come to help to identify what was the universe like at the beginning, what is it like now, and where are we going? How was it made up? Is half the universe made out of antimatter? What is dark matter? What is that 90% of the universe that we now know exists, but we don't know what it is?
Okay. Well, tell us a little bit about yourself. How did you get to this point in your career? Where are you from?
I'm from all over the Midwest in Texas. I went to the University of Texas, have an aerospace engineering degree, have a master's degree in business administration from the University of Houston Clear Lake. So why would I be working with a bunch of physicists? Well, mainly because NASA has the responsibility to do the project management and integration of this high energy physics experiment. So as an engineer, I have to work with 600 physicists, engineers, and technicians across the globe, most of them being funded by other agencies, to work together to build this experiment, to operate this experiment. It's a very interesting process, and it's been a learning experience for me.
Tell us a little bit about what it was like growing up as a kid when you grew up, and did you ever think you might be here doing this?
No, absolutely not. I grew up in small towns. Um, Never thought I would ever say that I've been to as many foreign countries as I've been to. Um, no, there was no way that as a kid I ever said I would be doing this, but NASA has afforded that opportunity because of the international collaborations that we have, in particular with this International Space Station. AMS is interesting in that we have as many countries as the space station has countries, but they're different countries, and they're typically not the space institutions, so um, they're not JAXA and those types of agencies. Instead, they're the physics institutions from those different countries. So certainly, I've met a lot of people, um, very interesting people that are learning things about this universe that there's no way I ever thought I would be part of that.
Okay. Tell us a little bit about why AMS can take advantage of the space station. What's important about the space station for being able to conduct this experiment?
So the biggest advantage that we have with the International Space Station is that the space station provides us power and data. Um, if we had to provide that on our own, if we decided to make the AMS a free-flying satellite, we would have had to have provided our own communication systems, our own power systems, our own um, data systems that we currently get from the International Space Station. So that allowed us to focus the amount of weight that we had available to launch into science. So more detector weight uh, basically means we get better science because we're on the International Space Station.
Okay. Hey, we had a couple of Twitter questions. We advertised your interview in advance, and we got several different good questions from folks out there. I'd like to ask you those right now, and the first one is pretty basic. It's from Corey McDonald, and Corey asks, how many particles has AMS collected?
So that's a fairly easy question to answer, and actually you can look for yourself. If you go to ams.nasa.gov, I put a particle counter on the front of our website, and I just looked just prior to this interview. We are currently at 12.8 billion particles measured. We are measuring at a rate of about 1 to 1.2 billion particles per month on AMS. We're measuring particles 24 hours a day, 7 days a week, 365 days a year, 366 this year. Um, and we have a cadre of operations team in Geneva that are constantly monitoring the payload, making sure that thermally and electrically everything is going smoothly, and making sure that the data is coming down through the proper systems and making its way to the science community.
And that's billion with a B, right? A big B.
That's
Is that
billion with a B.
more or less than you were anticipating?
We actually are measuring a little bit less than 2 times what we expected to measure. We were a little bit surprised when we first got up there and we started measuring data at a rate a little bit less than twice what we were expecting. We've managed to uh, deal with that in our systems. We had some robust capabilities in our systems that allowed us to handle that. We've done some things to ensure that we're not overwhelming the space station data systems. Um, but at times, we are using as much as 1/3 of the bandwidth coming down from space station, particularly at night when we're not downloading video. We can burst down AMS data and get it to the scientists in Geneva.
Wow, double the data. The next question comes from Morgan Spice, and I'm using their Twitter handles here. I don't know if it's their real name, but they're asking, do you think it's possible that our Big Bang is just one of many ongoing Big Bangs?
So that's an interesting question, and AMS most likely will not be able to answer that question. We can look back almost to the beginnings of the universe with AMS over the time frame that we expect to be on the International Space Station. Essentially, the longer you're there, the further back in time you're looking. Um, so with that, we can see back to the origins of this universe, maybe back to the beginnings of this Big Bang. If there are multiple Big Bangs, we just won't know that answer from AMS.
And you talked about the potential for the instrument. The Hubble Space Telescope basically rewrote the books on visible and other light ranges in astronomy. Do you anticipate that AMS could have that same kind of effect on our understanding of the universe and our thoughts about astronomy?
So AMS at times has been called the Hubble telescope for charged particles. The reason for that is because over the last 50 years, we've done a tremendous job of studying uh, light rays, uncharged particles. What we haven't done a very good job of is studying charged particles. So with AMS, we built a system that has, I like to say, if you got every high energy physicist into a room and you had them pick out which detector they would put on a high energy physics experiment, we put all those on a list and we put them all onto AMS. So with that, we have the capability to measure a single particle in multiple ways, usually multiple times with different detectors. So with that, we'll be able to um, look at each particle, identify it, and ensure that the data that we're getting is accurate. With that accurate data, we hope that we'll be able to potentially redefine what we know as high energy physics today.
And any idea on when we might be able to hear some of those results? I know that there's a lot of peer review and everything that goes through that. Can you explain that process to us?
So the AMS collaboration, as I mentioned before, is made up of 600 physicists, engineers, and technicians from around the world. The way that the group works is they take and separate those into two separate physics research groups, and they take the data as it comes down, the raw data, and each one of them takes the data and analyzes for particular things. They get back together every once in a while and say, well, let's look at this area, let's look at that area, but they want an independent verification of that. That's what we do within our own team. Once that is finalized, we go out for publication, and so that will happen. I don't know when. With 12.8 billion particles so far, it's a lot of data to go through, and so I certainly would expect that sometime, within the next year or so, we would have some data coming out. We certainly have a lot of potential with the 12.8 billion particles,
And you're still collecting more.
1.2 billion particles a month.
Okay. The last question I'm going to ask you today, and thanks again for being here, is as someone from humble beginnings, do you have any advice for kids or students or folks out there that think they might want to get involved in this in the future? When you grow up in a small town or even a big city, and you may have disadvantages, what do you need to do to get through school so that you can take advantage of these kinds of opportunities that might be out there?
Yeah, the biggest thing that this question comes up sometimes, and the biggest thing that I always point out is you just have to continue studying your math and science. Um, Go get an education in an engineering discipline or a science discipline, and go out there and try. You never know what's going to happen.